Hey everyone, Miss Butler here. I have a video on periodic trends and explaining them for the AP chemistry level. Okay, this handout, the do's and don'ts of periodic trends, is going to be a huge thing for you when you're working on periodic trend practice problems and when you're studying for the test. If you don't have a copy of this, you will get it soon, I promise, but it's also posted on Canvas for you. I just want to talk about a few things and we'll go over it more in depth in class as well. But you're probably going to see periodic trends on a free response question, probably multiple choice too, but this is really focusing on the justify your answer or explain your reasoning. So you might see things like this. A statement such as, in terms of atomic structure, explain why the first ionization energy of selenium is less than that of bromine. Often these questions are not well answered because students simply state that the trend, such as ionization energy, increases as you move left in a period, but they don't talk about the forces that created the trend in the first place. You have to talk about the forces that create the trend and avoid the impulse to simply use the location on the periodic table as an explanation for the observed property. If needed, chant over and over, a trend is an observation, not an explanation. A trend is observation, not an explanation. You are allowed to state the trend in your answer, that ionization energy increases as you move left, but you must also go further by explaining the causes. So we need to talk about forces, and you also have to talk about both the atoms. So in this one, we would have to talk about selenium and bromine, not just one of them in your answer. If you just leave one or just talk about one, you're implying about the other, and you will not earn any points. So almost all the properties that we're asking about are going to rely on Columbic attraction, which is the same as electrostatic attraction. And so we will talk about that in some of these slides. Okay. One other thought I would say is when you're looking at these, it's always good to state the definition. So if we're talking about atomic radius, give me a little summary of what the definition is. The last question up in the example was ionization energy. Kind of explain what that is in your response and then give me the do's for the justification. These don'ts are supposed to guide you as to what not to do or what common student mistakes are. So you are trying to follow the do column when we're talking about going across a period or down a group. So here's some more trends on that page, a few others, and the last page, and some final thoughts and tips for you. So again, this should be something, I know it's very wordy, but something that you read and treat like notes, highlight it, mark it, and this is essentially a study guide or a cheat sheet packet in explaining periodic trends. All right, so this is AP Chem. We're not just going to say as you move up and to the right, the trend increases, or as you move down to the bottom, it decreases, things like that. We need to have reasonings for these patterns and trends. So what you're going to do is you're going to talk about Coulomb's law, which is also electrostatic attraction. AP or College Board has used that phrase instead of Coulomb's law lately, electrostatic. You're going to talk about Zeph and distance. You're going to talk about repelling electrons and then minimizing electron-electron repulsion. So we'll take a look at all of those and what they mean so you can talk about them and act like you know what you're talking about. All right, so the first big thing we need to talk about is Columbic attraction. And on the last 2 years, the AP exam has used electrostatic attraction or electrostatic charge as a synonym for Columbic attraction. But essentially, it is the attraction between oppositely charged particles. So if I have a particle here and a particle here, and we have a certain distance between them, Columbic attraction is equal to a constant times the magnitude of the first charge, which is usually positive, and the magnitude of the second charge, which is usually negative, and r squared is our distance between those particles. Okay, could we have Columbic attraction or Coulombic repulsion if both of these were positive? Yeah, 2 protons will repel each other. 2 electrons, negative and negative, will repel. But often with periodic trends, what we're talking about is the nucleus, which is positive, and the electrons, usually the outermost electrons in particular, which are negatively charged. You do not need to use this equation on the AP exam, but we need to understand the relationships. In an atom, if I increase the number of positive positive protons in the nucleus, I am going to increase the amount of Coulombic attraction. Think of a magnet. If I have a stronger magnet, there's going to be more attraction to the negative electrons. Also, if I increase the distance, so maybe I have my nucleus, but my electrons are now moving farther away. They're farther away from the nucleus. When I increase the distance between the nucleus, the positive nucleus, and the electrons, my Coulombic attraction goes down. Picture magnets again. If I move those magnets far away from each other, there's less attraction between them. All right, here's a new concept that's very important. It's called effective nuclear charge, and we use ZEFF, Z-E-F-F as the abbreviation, effective nuclear charge. And what it is, it's the measure of the attractive force of the nucleus. And so the reality is, I have an atom, and you can picture the old school Bohr model with the rings of electrons around it. But that nucleus has a level of attraction that the electrons can feel. But remember, there's some, if you picture those rings, there's some electrons that are close to the nucleus, some that are farther away. So we really are trying to measure the effective force of the nucleus on those far out electrons. So here's how it works. We are going to take the number of protons in the nucleus minus the number of core electrons. And core electrons are the ones on those inner rings if you picture the Bohr model. So I am getting rid of essentially the number of protons minus the core electrons leaves me with really the number of valence electrons. That is what ZEFF is. So group 1A, meaning the first column on the periodic table, if you think of like sodium, for example, sodium has 11 protons and it has 11 electrons, but 10 of them are core electrons, and 1 is a valence or an outermost electron. So 11 minus 10 gives me a ZEFF of 1. So the effective nuclear charge of the first column, the alkali metals nucleus, is 1. And so as we move over across a column, across a row or a period, we are adding more valence electrons. So this stays the same, the core electron stays the same, and so what we're doing is we are increasing the ZEFF. So by the time we get all the way over to the halogens, the ZEFF of the halogens is 7, because we take the number of protons minus the core electrons and we're left with 7. The higher the ZEFF value, the greater the attractive force of the nucleus is, meaning the electrons are held into place tighter by the nucleus. And so we are trying to relate this to energy and Coulombic attraction. If an element has more ZEFF, that means there's more attraction to those outermost electrons. Another very important factor that we're going to look at is how distance impacts the periodic trends. So as we increase distance, the attractive forces between the nucleus and the valence electrons are going to go down. So let's relate that to energy, to Coulombic attraction or electrostatic attraction. If I have an element like lithium here with 3 electrons, I'm measuring the distance from the positive nucleus to the outermost electrons. Versus I have potassium here from the outermost electrons to the nucleus. There's clearly more distance here. And so because there's more distance between the outermost electron and the nucleus, there is less electrostatic or less Coulombic attraction between the nucleus and the outermost electron. More electrostatic here because the electron is closer. All right, another topic is repelling electrons. And so if we have electrons in the core, those core electrons, they technically shield the nucleus from those valence electrons. So we have essentially these core electrons kind of blocking the positive charge of the nucleus from those valence electrons. Be careful with shielding or repelling electrons because we only use shielding electrons when we go up and down a column, not across. So basically in a sublevel, meaning if I have the 2s and the 2p electrons, there's not much shielding happening between those. But do the 1s and 2s electrons shield the 3s electrons? Absolutely. So relating it to energy, essentially I have these inner electrons are blocking this positive charge from the valence so it doesn't feel its full potential. That's why we use ZEFF. So ZEFF is measuring how much this electron feels because it's being shielded by these guys. Versus if something doesn't have any shielding or core electrons, this valence electron feels the full pull of the nucleus. This one does not feel all plus 3 because it is blocked by those two inner electrons. All right, when I think of shielding electrons, I think of dodgeball. You've all played dodgeball in gym, and so really the shielding electrons are just like dodgeball. When we play dodgeball at gym, you have these big, tough, strong guys that will be in front. They'll run out and grab the balls, right? And maybe you have the scrawnier kids that are going to hide behind them. Well, the goal, if you don't like to play dodgeball in gym, if you're hiding behind these big, tough guys, right? If I hide behind those, they will shield me or block me from the dodgeball, from the nucleus. So the valence electrons are the scrawny guys hiding behind these tough ones. All right, one other thought is atoms are going to try to minimize electron-electron repulsions. So when electrons are paired up in an orbital, there are some electron-electron repulsions. So atoms are actually more stable when they have unpaired electrons. We know that it will follow Hund's rule. We'll do one at a time before they pair up, but some atoms have to pair up. How can we relate this to energy? So and the trends. So let's look. On this one, we have electron-electron repulsions that will happen in this 2p sublevel. So if I'm looking at the 2p sublevel, the element that has 3 electrons in the 2p sublevel is nitrogen, and this is oxygen. And so what happens is oxygen has more electron-electron repulsions than nitrogen. So when we're talking about trends, it might be that oxygen is more inclined to lose this electron to eliminate that repulsion that is happening. Whereas it might be easier to remove the electron, or it might not attract electron, or it might attract electrons to try to get more paired up and have a full subshell, things like that. So basically, an atom, when it comes to the trends, you might see some changes or like anomalies where we would expect a lot of attraction to this electron because there's more Zeph in oxygen than nitrogen, but the reality is due to the electron-electron repulsions, it actually is going to be more likely to be removed. Let's look at this little question here. Which pair of charges feels the strongest repulsive force? So take a second, check this out. All right, so it looks like we have equal distance, a negative and a positive. We know that's going to be attraction. A negative and a negative, so we have repulsion here. 2 negatives and a 2 negative, so this will repel more because they're more greater magnitude, same distance. And lastly, positive, positive, big magnitude and half the distance. So the biggest repulsion is going to be happening here because it has the bigger magnitude charges and the smaller distance. Think of Coulomb's law. The bigger the magnitude the charges and the distance is on the bottom, so the smaller the distance, the more usually the attraction, but when the charges are the same, the bigger the repulsion. All right, let's talk about the first two trends. Atomic radius. Atomic radius is thought of to be the size of the atom, but how they actually measure it is they take half the distance between 2 adjacent nuclei. So they make a crystal of the element, so 2 atoms bonded together, and they measure the distance from one nucleus to the other and take half of it. That is how they measure atomic radius. Ionic radius, so if we have an atom that loses electrons, they are now a cation, positive, and smaller in size than the neutral atom. And if an atom gains electrons, they will be negative, an anion, and larger compared to the neutral atom. All right, here's a little example. Atomic radius of alkali elements and ions. So we're going down the alkali metal column. You can see that the angstroms, which is a measurement for distance, is getting larger, and same with the picture. So let's look at the do's and don'ts. For atomic radius, when we go down a column, it says increased number of energy levels increases the distance over which the nucleus must attract and therefore reduces the attraction for electrons. Full energy levels provide shielding between the nucleus and valence electrons. Thus, within a column, Zeph is constant. So these have the same Zeph, so we look at distance. There is more distance between the nucleus and the outermost electrons, so the atom gets larger, the atomic radius gets larger. Now let's look at the ions. These are all positive ions because these are alkali metals who are likely to lose an electron. So positive ions are smaller than their respective neutral. Look, 1.23, 0.68, 1.57, 0.98. How do I explain this? Well, positive metal ions result from the loss of valence electrons. In many cases, this means that the outermost electrons are now in a smaller principal energy level, and thus much closer than the electrons in the original neutral atom. If the entire set of valence electrons is not removed, there will be decreased electron-electron repulsion between the remaining electrons, allowing electron cloud to contract. So first of all, if we have our alkali metal here, and I remove the electron to form a +1 charge, I went from 1s2 to s1 down to 1s2. So we are now smaller because we have less distance between the nucleus and those outermost electrons. If we have something like this, and I remove one of the electrons, so I started, pretend this blue one was there, the one that's crossed off, this one counts now. So we have 1s2, 2s12, and 2p123. If I remove one of these electrons, now I'm at 1s2, 2s2, 2p2. And so because there's less electrons in this 2p sublevel, the electron cloud is able to contract. Picture yourself sitting on a full couch and someone gets off. What happens when you have 4 or 5 people sitting on one couch and one person gets up? Everybody kind of adjusts, picks their butt up, moves to give themselves more room. That's what the electrons do as well. When the one electron is removed, the cloud is going to adjust, and it's allowed to get a little smaller, a little closer to the nucleus because there's one less electron present. Same idea here, but these are the halogens. So when I go down, we get larger because we're adding more energy levels, so there's more distance between the nucleus and the outermost electrons, making the atom larger. And then for a negative ion, a negative non-metal ion results from the addition of a valence electron, so there's increased electron-electron repulsion, so the electron cloud expands. Same idea with the couch. If you have 2 people sitting on a couch and a third person joins, you all kind of have to move over and stretch out, right? That cloud has to expand slightly when we add these extra electrons. So you can notice the negative ion is slightly larger than the neutral atom. All right, here's a good vocab word. Isoelectronic means these atoms have the same number of electrons. So oxygen normally has 8 electrons, but when we gain 2, there are now 10 electrons. Fluorine normally has 9 electrons, but when we gain 1 electron, we have 10. Sodium normally has 11 electrons, but it formed a positive charge, so it lost an electron, that's 11. Magnesium has 12 electrons when it's neutral, but it lost 2 of them, so we're at 10. And aluminum, same idea, lost 3 electrons. So all of these have 10 electrons. And what we notice is that even though these all have 10 electrons, the atoms that had to lose electrons are much smaller. The ones that lost more electrons are the smallest in size, and the atoms that gained electrons are bigger in size and bigger in atomic radius. All right, ionization energy is the next periodic trend. It's the energy needed to overcome the attraction between the positive nucleus and the negative electron. Think of it as how strongly an atom's nucleus holds on to its valence electrons. So this is the stealing or removing electron measure. If an element has high ionization energy, that means the atom has a strong hold on its electrons, high Columbic or electrostatic attraction, okay? And so it's less likely to form a positive ion. It takes a lot of energy to remove or steal that electron. Low ionization energy is the atom easily loses the outer electrons. It will form a positive ion, so there's not a strong attraction or hold on those outer electrons. All right, I want you to try to make a graph of the ionization energy versus atomic number. So a couple of thoughts. Coulomb's law is going to drive this graph. So really we're looking at, for up here, this is like going to represent our Zeph, the number of protons minus the core electrons, and down below is our distance. So let's just say for hydrogen, atomic number 1, I'm going to start us at 10, just so we have a starting point. All right. Now, when I go to, this is helium, my Zeph is going to increase by double on top because I have a Zeph of 1 for hydrogen. Helium has a Zeph of 2. Okay, the distance, the bottom, is going to be the same because both of those are in the 1s sublevel. So if the bottom of my equation for Coulomb's law stays the same and my top doubles, I'm going to be up double what we started at. Try to make that as straight as possible. Okay, now we go down to lithium. Here's what happens. I have a Zeph of 1 again, so back to this level of 10, but my distance increases because we add the 2s sublevel. So I'm guessing that lithium has less ionization energy, less attraction than hydrogen does because it has the same Zeph but more distance, so the bottom is bigger. I want you to try this for elements 1 through 20, make the graph. Remember, as we go across, we add Zeph, so we're adding attraction, but then when we go down to the next row, we're going to have to drop off because we're adding more distance, and more distance means less attraction. Pause the video and try to make this graph. All right, here is the graph with ionization energy versus the atomic number. Hopefully it is what you expected or sketched on yours roughly, that we have increases for each row, but then we have drop downs as we go to the next level. There are a couple exceptions I see, right? We would expect this to inch up and up and up. We'd expect this to inch up and up and up. Let's look at this green exception here, going from 4 to 5. Atomic number 4, is beryllium. And atomic number 5 is boron. So we would expect that when we add the protons, we would be adding or increasing our Zeph. So ionization energy, the energy needed to remove an electron, should go up because there's more attraction. Let's look. Beryllium's outermost electrons are in the s sublevel, 2s2, and borons are 2p1. So the s sublevel, remember, is a sphere. The p sublevel looks like this dumbbell. If I draw those on a nucleus, what we can see is that the p electrons are not penetrating the nucleus as well as the s. These p electrons could be up here and down here, not as close to the nucleus, so they're not as tightly held. So we see a little dip when we first go from s to p. Look at the other exception. We have a drop down from 7 to 8. That's nitrogen to oxygen. We're adding protons, so Zeph goes up. We should have more ionization energy. Let's look at the orbital energy diagrams in that 2p sublevel. N is 2p123, O is 2p4. And so what happens is O experiences electron-electron repulsions in this 2p sublevel. And those electron-electron repulsions within the sublevel mean that this electron is not held as tightly, so it's easier to remove, less energy to remove it if there's less attraction due to those repulsions. So we see a little dip once we start pairing up electrons. All right, one other concept with ionization energy is that we can have successive ionization energy. So IE1 is the energy it takes to remove one electron. IE2 is the energy it takes to remove a second electron, third electron, fourth electron. What's cool about this is it gives us a lot of information about the number of valence electrons. Okay, so as we go, we obviously would expect that as we remove electrons that the numbers get bigger because remember, as we remove, the atomic radius gets smaller, the electron cloud shrinks in. But what we also notice is a big jump that happens when we start to remove a core electron. So I drew a Bohr model for magnesium here with 12 electrons. I removed the first, I want my pen back. I removed the first electron. That's this ionization energy right here, 736. I remove this second electron, 1,445. Now when I remove a third electron, look at how high we jump up from 1,000 to almost 8,000 because I'm now taking a core electron. It takes a significant amount of energy to remove a core electron. So this guy in orange is showing the difference. For sodium, 1 valence, now I remove a core electron here. 2 valence, the third one we remove is a core, big jump. Aluminum has 3 valence, and we go from almost 3,000 to almost 12,000, big jump. So you can see once we start removing core electrons, there's a large jump, and based off when that jump occurs, you can identify how many valence electrons an element has. All right, electron affinity is the energy absorbed or released when electron is added to a gaseous atom. So is there energy, is it endothermic or exothermic when I add an extra electron? Negative electron affinity means it's exothermic, so that means the negative ion is more stable than the original atom because we released energy when the electron was added. A positive electron affinity is endothermic. That means the nucleus is not as effective at attracting electron. We had to force it in. I had to put in energy. We know about oxidation numbers. These are the positive or negative numbers, which tells us how many electrons will be gained or lost when it forms a compound. And then electronegativity is the ability of an atom to attract electrons in a chemical bond. So the bigger the electronegativity, the greater the attraction for those shared electrons in a chemical bond. So here are the patterns, and remember on the AP exam it's all about why. So we're talking about distance and Zeph and shielding. We're not just going to say ionization energy increases when we move to the right and move up. We're not going to say atomic radius gets bigger, big fat francium down here, bottom left, right? So we can use those to help us kind of as a trick to figure out the correct answer on multiple choice, but if it's a free response, we need to be able to explain why. All right, so you have some multiple choice practice problems. We are going to do those together in class, so just hang on to those. Hopefully this was an AP level explanation for periodic trends and helped you out.